Hello, in this presentation, I would be designing a fuzzy inference system for the problem of motion planning for multiple autonomous vehicles. The introduction to the problem in general is a different presentation which should be available somewhere in the video description. So fuzzy logic, as we all know, is a very fast system. In general, the planning technique is known as a reactive planning technique, where I have got some kind of robot or some kind of vehicle in a environment, in some kind of map where there are some obstacles. It simply takes in various distances, various metrics to quantify this environment and immediately decides where it needs to go as a unit move. So let's say it moves here, and the same thing repeats. It again takes in all the percepts from the different parts of the map, all the different inputs to decide the immediate next move. And if we are specifically talking about fuzzy inference system as a reactive planner, what it does is that it uses some human-fed rules in order to map these percepts or these inputs into what would be known here as the steering and the speed, or into outputs. So they are very fast, but the obvious problem is that they are neither complete nor they are optimal. In fact, the most that you can do out of such reactive planning technique or fuzzy inference system is, if you've got a single obstacle or sometimes two of them, you can design an optimal way to surpass this obstacle. But obviously this is not very general. If I have got very exciting things going out over here, some nice little grid out here, they would be neither be optimal nor be complete. And that would be the key challenge in this. How do we use this framework in order for multiple autonomous vehicles to navigate within an environment? Now, in general, a fuzzy inference system solution to any problem would have three aspects. There would be some inputs, there would be some outputs. These are the two things that we get in any system in general. There's always some inputs and there are always some outputs, but here there are always rules that a human writes, and the rules basically denote how the inputs get mapped to the outputs. So the underlying logic, the underlying mechanism of how the inputs are related to the outputs, it is by rules which are fed in by a human. So first we'll be looking at, in this presentation, what are the inputs. Then we would be looking in the outputs for this system are clearly two, so we do not need a separate slide for that. The first thing I need to decide is how to steer, whether to steer clockwise or anti-clockwise, and in any case, by which magnitude should I steer. So the first output will be the steering action that I have, and the second output would be the speed action that I have. And this we get it very naturally. Imagine while you are driving, you basically have a steering in your hand, by which you change by which you steer left or right, navigate around the road, and you've got brake and the accelerator by which you do some kind of speed control. This is of course a simplified version of a problem that I'm dealing with, so I'm not taking the two separate, as well as I'm not taking clutch and the gears, the system and all those things. So in the simplified version of the problem, I've only considered two things: the steering and the speed. The other controls of course may be fixed in using some best driving practices or some other system. Here I would only be dealing with these two systems, which are steering and the speed. So effectively I would first be looking at the inputs, and then I'll have a very brief comment about the rules. Now, what inputs do in a system is that they are a representation of the entire scenario. So if I have a vehicle scenario like this, I know that there is a vehicle here, there might be some obstacle all around, they might be in some vehicles like this, there might be some other vehicle ahead, there might be a vehicle at the back. I'm planning for this vehicle. So now this is a very rich set of information. You see that there are too many obstacles, there are too many vehicles, there are road boundaries, there's some position out here, there's some kind of road shape, there's a road geometry. There's too much of information out here. What I need to do in deciding what are the inputs to my algorithm is that all this rich set of information and all these exciting things happening out here, I need to convert them into few real numbers. And I need to be very clever in how I select these real numbers. Anything that is not represented out in these real numbers is completely lost. It's like the vehicle or the robot gets blind into whatever is not represented in these real numbers. If there are multiple things that map onto the same real number, then the robot basically cannot differentiate between these two things. So even though there's a terrible loss of information, I'll lose out all these rich dynamics which is happening out in this scenario presented, which I have drawn out here. I basically need to do that. I need to convert this rich dynamics into a set of real numbers, and for this presentation, these are the real numbers that I have chosen, and I'll quickly guide you through them. Basically, we know from uh, a very general driving system, all that we need to do is to maintain ourselves in the direction of the road. If we say we are not, there are no obstacles, there are no other vehicles, so all that we need to do is we need to maintain ourselves in the orientation angle of the road. So here we see that the road is in this direction, I'm in this direction. Here we see that the road is in this direction, I'm only drawing one boundary, but I am here. So I know there is an error. While my general road was like this, I'll need to do something. I'll need to turn left, or I'll need to turn anti-clockwise. So that is my first input, which is a very natural input. If I only take this one input, I'll be able to drive on very wide roads which do not have any obstacles, but obviously there are obstacles ahead all around. So I need to embed their information as well. I take distance from obstacle from the left, right, and the center. So I have taken distance from the left, right, and the forward direction. And these are my three new inputs. All that they will enable me to do is to decide how to steer in order to avoid an obstacle. And here even the road boundaries act like obstacles. So if I'm going very near the road boundary, I will come to know I have coded this information as some input. So if I'm going very near the left boundary, I will go a little away, I'll steer clockwise or I'll steer right, and correspondingly with the other boundary. So I have formulated a mechanism to take in distances from obstacle and encode them as real numbers. Now remember, when I say that I have only taken the forward, left and right distances, my robot is blind to this obstacle here, it cannot see this obstacle out here, it cannot see these two vehicles out here, it cannot see the vehicle behind, because these are the only three inputs that I've taken, and all the decision would be made, the instantaneous decision would be made only based on these three inputs. And one thing that we observe in natural driving is that there are always roads, there's always a marked lane. It may not be a physical barrier. In case if it's not a physical barrier, I can normally drive a little this side on the road, but it's not generally advised to. So the input side, it says that if I'm driving in the wrong side of the road, because I was allowed to, by what margin am I driving in the wrong side? This is my input side. So these are the various inputs I'll figure them out in this next slide. This is the slide which more formally says what is my angle of deviation, my input. I'm taking the left distance from the two corners and I'll basically be taking the minimum of them as my actual inputs. I'm taking the right distance across the two corners, I'll be taking minimum as the actual input, and I'm taking the front distance from 2 points, I'll be taking minimum as the actual distances. So all those the distance inputs I have measured from both corners twice, and I'm taking the minimum of the two. Now there are two more inputs that I have added in addition to these. The first is a strategy input. Now what happens that if I have a vehicle, I see an obstacle right in front, right here. For us, it becomes very apparent that it will go towards the right, but remember what the vehicle says or what the robot says, the information has been encoded in these real numbers. So I say, and based on this, it is not very easy for the robot to decide whether to turn like this or to turn like this. So I have added another strategy input that I will be deciding to denote whether I overcome an obstacle from right or left. The other scenario can be like this, where in this the robot should avoid from the left. So that is how this this is something that I have additionally added as a strategy variable that will enable my robot to decide whether to avoid an obstacle from the right or left. And the last input, which I'll take it here, the last input is the cooperation input. Now remember, my basic fundamental was that if there is a vehicle here which needs to overcome this vehicle here, of course it will overtake like this if this is a fast moving vehicle and this is a slow moving vehicle. But similarly, this vehicle should dip a little towards the side, which I called as was the cooperation, the amount by which it dips on the left side. This was how I defined cooperative overtaking to be. Now my vehicle is only seeing the front distances and the left and the right distances, and why it's seeing only that? Because that's how we normally drive. We do not look at anything behind and decide how to overcome it, because we know that what is behind is left behind. So my robot, as per the input so formulated, is completely blind to this vehicle behind, and hence I cannot by default have any kind of cooperative behavior. So all that I have done is I have added another input that will request this vehicle to move somewhere towards the right, somewhere towards the left. Similarly, if there was another vehicle coming here which I wanted to move towards the right in order to make overtaking feasible, this would be through a strategy input called as requested turn. So from a general strategy point of view, whatever I could not represent as continuous valued inputs, I have added externally to the system as strategy inputs. In the next couple of slides, I'll be explaining how are these inputs decided. This we all know, they can be measured very easily. So anything that my robot was blind to, it could not decide, I have externally added as my strategy inputs. And this is the first of the two inputs that I had. I saw an obstacle in front. My left recorded something, my right corner recorded this thing. The smaller is these two. Now based on these two inputs, based on these two values, or based on these two distances from the obstacle directly ahead, I can very easily decide whether I need to turn clockwise or anti-clockwise, or I need to turn left or right. And a very simple rule is that if the right distance is larger, turn right. If the left distance is larger, turn left. A very simple way to look at it would be that the right distance is larger, that means there's something good on the right, that means I should turn right, so that my left distance, which is smaller, will grow larger and larger. And as you can see, if this vehicle goes actually turns right, my vehicle orientation will change and then this left distance will get larger and larger. Another way to look at it would be to formulate various scenarios that the vehicle can do, which is what we have done here. Here we see this hypothesis holds. Here we see the left distance is larger, so turn left or turn anti-clockwise, and this is the right strategy. If there's an obstacle, the right is larger, turn anti-clockwise, and we can see the obstacle is directly ahead. The vehicle will go somewhere like this, so the strategy holds. And similarly here, if there's an obstacle towards the right, I will turn left or I'll turn anti-clockwise. Now this is just a hypothesis, it does not hold in a number of scenarios. In fact, if I have got odd looking obstacles which are very deceptive in nature, if I've got a very big obstacle like this, and let's say the road was very bad, it naturally does not hold. The vehicle will try to turn like this. But the problem was that I needed some very quick and dirty method to find out the inputs to those two strategy parameters. It's a reactive planning technique. There's nothing very smart that I can employ in my reactive planners. I cannot do a lot of computation in my reactive planner, so there was some quick and dirty method that I need to find out. I use this heuristics. Now, given most of the practical roads where the obstacles are not really that bad shaped, where there are not too many large obstacles, there's only such obstacles like this heuristics holds. So, one of the strategy inputs that I have been able to fix in my values to, apart from straight roads, the one of the strategy inputs I have always said in this slide. How do I fix in the value? The other one I'll be taking up right at the very end. So apart from straight roads, a very common thing that the vehicles come across is crossing scenarios where you've got roads intersecting like this, where a vehicle may need to go like here, here, or here. So we tried that can we use the same kind of fuzzy inference system for navigating such kinds of scenarios, and the situation was very simple. First of all, what I would be presenting later on, how a vehicle overtakes another vehicle, it's not valid in crossing kind of scenario, so the overtake is disabled. Another thing that some traffics have traffic lights, when in which case you need to look at the traffic light and then decide whether you can go or you need to stop. Some do not. If you do not, then there is a very good system which is first come first serve system, which means the vehicle which came into the region first will exit the region first. It will have a greater say. That is what we implement. The vehicle tracks down all the other vehicles. It sees if there is a vehicle which was already there, it should take priority. It should go first, else I will go first. And now, as we would understand now, that if I need to go from here to here and I use my general crossing scenario to carve out a road like this, my vehicle is out here. I have of course sensed in an obstacle right at the front, but now if my right obstacle scan would have been greater than my left obstacle scan, then I would have said I'll turn like this. And if my left would have been greater, I would have turned like this. So it does not hold in this kind of flat road scenario, which means in general that I can navigate through curved roads like this. My very general vehicle will be able to navigate like this, but it cannot navigate roads like this where there's a flat end. So in order to solve this problem, I superficially introduce a small barricade in order to give it a little curve, and now when I scan my right, it will be larger and it will automatically turn towards the right, which is the right thing to do. When it will come here, after turning a little right, again right would be smaller, it will turn like this. When it comes here, now it does not need to turn anyway, it just needs to go straight. So that is what my crossing scenario is all about. And now what we have, I had to frame in the inputs, I had to frame in the outputs. The outputs are of course only two outputs, there are no much choices to it. The outputs were the steering and the speed. I designed in a number of inputs, and now all I need to do is I need to design in rules which will map my input to the output. Now a lot of time we face in this problem in how exactly to write the rules, and the design methodology of a fuzzy inference system design in general, it's not simple. What mostly we do in modern times is that we let an optimization technique like genetic algorithm design the entire system for ourselves. In fact, that's what many of the modern publications are all about. People only say what would be the inputs and outputs, and they leave it up to the fuzzy up to the genetic algorithm to give you a final inference system, which of course I'll be taking a little later on. But it is not entirely possible because there are too many inputs. There is a rich scenario, a rich traffic scenario. There are too many things that can happen. So I need to follow the classical fuzzy design methodology when I frame in these rules or when I design in my system. The first part of the classical fuzzy inference system design we've already dealt with, that we've said that my rich dynamic information I need to codify in a set of real valued inputs. That's what we've already done. The catch here of course is they should be as less inputs as possible. If you take in too many inputs, or basically if you feed in extract out everything from the actual system and embed them as real number in your system, it'll become such a complicated system that you won't be able to design the rules. So these should be as less as possible. And similarly here, of course, I did not have a choice in the output, but if I do have a choice, then my output should be as less as possible. So suppose I have designed a few inputs like this, and I have a few outputs like this. Each of these inputs I need to further divide into membership functions. For the inputs that really play a big role, usually it's good to start off with 3 membership functions, but you follow less important inputs, it might even be advisable to start with maybe just a 1 membership function, which just gives you some trend, or maybe 2 membership functions. So again, I need to divide all the inputs and the outputs into membership functions, and the design methodology is same. They should be as less as possible, and they should be as less as possible. Once I do that, so let's say that one of my inputs was my angle of deviation from the road, let us say A, and I said my angle is very large, it is 0, or it is very small, and we know how we can and I had 2 outputs out here, and I said that my outputs are that steer too much on the left, steer too much on the right, and do not steer. And I know how these would be related by this thing. By a very simple rule, I can correlate both these inputs. I can simply say that if my angle is very large, positive, then my steering would be very large in the clockwise direction. If I have no deviation, then basically I'm driving left. There's no steering that I need to do. And if I have a very small angle, then that's what my rule would be. So each of these inputs we can correlate to the output by very simple rules like this. And that's all what the methodology is. But the problem is that this system, if we simulate, it will not work. Then so basically I just said that if we simulate the system, but of course will need to make a simulator for this. We'll need to be able to record all the inputs, take percepts, take some action, and see how the vehicles are moving. And when it does not work, we basically manually inspect the system, what were the inputs, what were the output produced, and then of course we need to do something to make the system perform. The first thing that we do is we fiddle around with the rules. We see if we can change in the rules somehow. I forgot to mention that even the rules need to be as less as possible. So first I try to fiddle around. I try to change in the rules. The second thing that I do, if changing the rules also does not make the system improve appreciably, I get better performance, but I do not get the best performance. The second thing that I do, each of these membership function, it's basically in the form of some curves like this. So I need to move them around, I need to elongate them up, I need to do something. So there's some fiddling around that I do in order to get the system to the desired performance. And you can basically see for which inputs the system is not performing, what was the expected output, which were the rules fired, and correspondingly you can isolate which membership function should I fiddle around with. If my step 2 also fails, it does not improve the system. The unfortunate thing is, as my step 3, I will have to increase the membership functions. It means that I have taken 2 less membership functions, so I might increase my membership function by 1. And correspondingly, as my step 4, I'll need to add in new rules. So my system was not working. I first fiddled around with the rules. Nothing happened. Things changed well and good. If they didn't change, I fiddled around with my membership functions. I moved them left and right. I expanded, contracted them. Worked well and fine. If it did not move, I had to add a new membership function. It did not work, I had to add in new rules. If I played around with all this well and enough, my system is still not working, then I basically do not have rich information, or I do not have rich action set. And that's a nightmare, that when you need to add in new inputs or you need to add in new outputs, basically everything changes when you add in a new inputs or you add in new outputs. There's very less that you can carry forward. So that's how the entire fuzzy inference system was designed for the previous problem. That's how the rules were framed. Now, of course, we had an iterative design methodology. We first considered only simple scenarios. We kept complicating, and we came up with a very small set of membership function rules. Then we kept complicating the scenario, kept up with more rules. So it's an iterative process that we find. But finally, we got in, after much of hard work, using this design methodology, a fuzzy inference system which works for all scenarios, which overcomes all benchmark, except for one problem, which will now be the main crux of the work. I have so far in general not dealt with the problem that there are multiple vehicles, and if there are multiple vehicles, there is something known as overtaking that should happen, that will not happen in the previous methodology. All the vehicles would be treated as static obstacle to try to avoid normally. So that's the problem of overtaking. Now, when it comes to overtaking, we see that the normal rules of the game do not work. The normal rules of fuzzy logic do not work. And why do they do not work? Now, overtaking is not a reactive planning technique, as in we do not say that I am here, there's a vehicle here, oh, I should overtake, and I decide to overtake. It does not happen like that. And because of which any reactive planning technique will not be able to appreciably do that. What instead happens is that I am here, I see a vehicle out here lying somewhere in the front. I ask myself, I think, and thinking is of course something very contrary to reactive planning technique. They do not think much. So I think whether overtake would be feasible or it would not be feasible. If it would be feasible, I do this. If it would not be feasible, I do something else. So basically, unlike reactive planning technique, where I was taking in inputs, I was applying the rules, and I was taking in the outputs, here I need to modify the design so that I take in the inputs, I think something, and based on whether it's positive or negative, I have got two different kinds of actions, which is of course overtaking or not overtaking. So first I would be discussing about this block, which is the thinking block of it. If this thinking block returns positive, I have what is known as an overtaking behavior, where this vehicle succeeds in overtaking this vehicle. If I do not have an overtaking behavior, I have got what is a vehicle following behavior, where this vehicle simply follows this vehicle, reducing its speed of course. This was a faster vehicle and this was a slow vehicle. So the first thing I need to do is this thinking block out here, which decides the feasibility of overtake. And the feasibility of overtake, I'll again draw this figure out here. I first consider a very simple example. When there are only two vehicles, overtake will always be feasible if two vehicles can come parallel to each other at any section of this road. So if the road was very narrow, overtake is naturally not feasible out here if the two vehicles cannot place themselves parallelly. It's infeasible out here, but it's feasible out here. So this is my first condition which must be true for overtaking to be taking place, but I know there can be other vehicles which complicates the scenario very much. I cannot work in that kind of complicated scenario using a very quick and dirty method. As I said, I need to decide this input based on very quick and dirty method. So I make in an assumption that my road is not that wide that more than three vehicles will come on road. I restrict my width. The only case that can happen in such a case is that if there was an oncoming vehicle like this which was either going here or coming here, this is the only case possible because my road is anyways not wide enough so that four or five vehicles can come simultaneously out here. Now, my overtaking would of course be possible if these three vehicles can align themselves such that they would lie all parallel to themselves with some safety distance. Of course, safety distances is what I haven't been saying, but they have been recorded at all steps. If this can happen, my overtaking is again feasible. So this would be my condition 2A, wherein three vehicles can place themselves parallel to each other, and it can, and as you can see, in the worst case scenario, this will come here, it will occupy this position, this will occupy this position, or let's say even if this vehicle is here, it will occupy this position, and overtaking would be feasible. Or I can have a road like this vehicle wants to overtake this vehicle, and there's a third vehicle which is so far ahead that I can easily overtake, and by the time I finish the overtake and lie somewhere like here, it would have only moved here with sufficient distance, and this would be known as condition 2B. So basically there are three conditions which must be true. The first is compulsory, that two vehicles should be able to lie themselves parallel to each other. So this was my condition. The third was that three vehicles, if there is an oncoming vehicle like this traveling in any direction, three vehicles should be able to lie parallel to each other, which was 2A. Either of these conditions need to be true, not both of these vehicle conditions need to be true. Or by the time that this vehicle completes in this trajectory and completes the entire overtake, the entire time that it takes to complete the entire overtake, this vehicle should be lying away from this overtaking region. So I'll draw this again. I'll draw the condition 2B again. I say the road was not wide enough for three vehicles to enter. This vehicle completed the overtake trajectory like this. This was the overtaking zone. By the time this vehicle lied here, some oncoming vehicle like this, it could only reach this position. So it could not even reach the overtaking zone. It could not even reach the overtaking zone by the time that overtaking completed. Or of course it was moving in the other direction, then it will not be completed. Now why do I call this quick and dirty method? That it takes me no time to compute all the various metrics associate. It takes me no time to compute everything that I have been saying. And why doesn't it take time? I make another assumption. I say that all vehicles would basically be traveling straight for feasibility computation with the same speed. So if this was traveling with V1, this was traveling with V2, this was traveling with V3, this was traveling with V4, in fact they might not be even parallel to the road, I say they'll be traveling straight ahead of the road in either direction that they are traveling. And so I can very quickly and compute approximately whether it would be feasible or not. There are wide margins that I have kept because this is an approximate because it's an approximation, there are margins that I have kept along all sides of the vehicle. So I'm basically computing for this vehicle, even though I'm saying that I have computed for this vehicle. There are margins front, left, right that I have kept. And even if I make the wrong decision, that my fuzzy inference system that drives each of these vehicles separately, all the vehicles may not actually have communication. They may strictly not have communication. Each of these, if a wrong decision has been taken, then my fuzzy inference system, normally by its normal design methodology, will do something so that collision does not happen, and that is what is applicable in many driving scenarios. If this vehicle makes in a very bad decision, the overtake is not feasible, then also the vehicles will adjust in some way so that collision does not take place. So either condition 1 has to be true, along with that either 2A has to be true or 2B has to be true. I make in the best of approximations, I make in the best of decisions to decide a judicious feasibility strategy by overcoming these approximation of straight driving vehicles by the extra wide margins. But even if the wrong decision has been taken, the vehicles will adjust themselves by the internal fuzzy inference system driving methodology to drive straight. So that was the thinking block out here that I have just presented. Now suppose the overtaking happened to be true. My thinking block said that overtaking is possible, and this vehicle can overcome this vehicle using any by the fuzzy inference system, by the normal fuzzy inference system. Now this vehicle has to cooperate and dip leftward. So that is how the requested turn strategy variable is set. It has to dip leftward, but this vehicle may or may not be dipping leftward. That is what I need to decide. If it dips leftward, it will be called as cooperative for this vehicle. If it does not need to decide whether it needs to dip in leftward, it will call as uncooperative for this vehicle. And basically I know if condition 2A was true, then the vehicle need to place themselves in parallel, and therefore it needs to dip leftward. So the turn has to be cooperative. The requested turn for this would be left. However, if the condition 2B was true, wherein this vehicle was overtaking this vehicle in a time that this vehicle was not even in the overtaking zone. Now naturally I need not do anything for this vehicle. It's not even reached the overtaking zone by the time overtaking is complete, so I need not request any turn for this vehicle. That's why the overtaking would be called non-cooperative for this vehicle. So that's a very quick and dirty method that I enable overtake to happen between vehicles. Assumption 1, not very wide roads. Assumption 2, vehicles driving almost straight. If my thinking block says no, overtaking is not feasible, which obviously means I need to follow the vehicle, which is very simple. My normal fuzzy inference system can treat this, basically follow this vehicle. It will not be allowed, it will not allow overtake, it will not allow this to move on the wrong side. That means it will be forced to follow this vehicle. However, overtaking might be possible at a later stage. So let's say the overtaking was infeasible due to an oncoming vehicle out here and it passed away. It moved to some new location like this along with time. Now overtaking is feasible. So an overtaking once infeasible can later become infeasible, and the new scenario that happens is something like this, and all roads are at least 2 lanes. If they are not even 2 lanes, then basically people tag them as 1 lane, disallowing traffic from both sides. So there's no way that overtaking would now be infeasible unless there's a new vehicle out here. If there is no new vehicle out here, overtaking has to be feasible. So we compulsorily make this vehicle overtake this vehicle. Along with time, its speed has reduced very drastically. In order to overtake this thing, it's simply following this vehicle ahead. So because its speed has been reduced to a very low amount, by following this vehicle not being allowed to overtake, we'll have to artificially enable the overtake to happen. So that's why we do two things. We say that now you need not stick on your on the side, now you can go to the wrong side to overtake, and you do not need to consider this vehicle in front, which will enable it to increase the speed to overtake. Now remember, if I do not go on the wrong side, I cannot overtake. I will have to go on the wrong side, even though this side is reserved for vehicles from this side. And if I do not increase my speed, I cannot overtake. I will have to increase my speed. So this is what these two exceptions do. These are purely exceptions added in order to make this overtake feasible. And by the way, again, there are safety distance which make sure the vehicles do not actually crash. And the last thing that I would be presenting out here, of course, unlike most of what modern literature says, it just says that make a genetic algorithm or make an evolutionary technique give you the final fuzzy inference system. We do not do that because the problem is too complex. There are so many variables associated, there are so many scenarios associated, we cannot even make a data set of all scenarios. So we came up with some fuzzy inference system that could surpass all the benchmarks that we said. We designed it manually at each stage, seeing what the problem is, seeing how the which input could be changed, which membership function could be changed, tuning that. So we, using that design methodology, we generated in a fuzzy inference system. But now, once I have gotten a fuzzy inference system, now maybe there's something that the genetic algorithms can do. So a fuzzy inference system, of course, has the inputs and the outputs broken down into some membership function, and it secondly has in some rules, which are basically in the form of, if angle deviation is very large, and then make that a very large clockwise turn. So I carry out the optimization of these two separately, because these are clearly very two different kinds of things. They are very two different techniques which will be used for tuning in of the membership function and the rules. So I first deal up with the first part of it, which is the tuning up of the membership functions. This is what my membership functions are like. If I simply make them move by a large amount, then I get problems that my new membership function convey very different meaning to the rules what my previous one would did. And plus, as we know that it's a problem of the optimization is multimodal in nature, and because it's so multimodal in nature, making too many changes would mean a lot of exploration, which will mean I'll basically end up at a random point in the solution space, or in the optimization space, or in the fitness landscape. So I say that my optimization of the membership function parameters can be only within a very small range out here. It can only increase the spread, or it can increase the spread, or it can move the stop by, say, plus alpha to minus alpha, where alpha is a reasonably small number. It's small enough to cause not to cause randomness, and it's large enough to make some optimization possible. And that's what I do. I suppose there were 5 inputs. They were, everyone had 5 membership function associated, and there were 2 outputs, each with 4 membership function possible. So there'll be these many membership function. For each, I vary the spread from minus alpha to alpha, and I vary the center from plus beta to minus beta. So I'll have these many into 2 number of genes that I list them out straight away. That solves one of my problem that I need to decide for solving any problem with the genetic algorithm. This denotes the membership function center. It will vary from minus alpha to plus alpha, and this denotes its spread. It will vary from minus beta to beta. And then my regular genetic operators would use this gene, or it will use this kind of individual representation strategy, this chromosome, to optimize it. And for the rules, I say, this was for the rules I'll take in here. If my deviation is very large, or if the rule was, if the angular deviation is very large, then make the steering turn by very large. My rules can only change from very large to very, very large, or from very large to large. So they can either upgrade membership function by 1 or downgrade it by 1. So if there were 3 membership function for my turn, they either make it membership function hop from here to here, or from here to here in its participation in the rules. And similarly for the outputs, if it makes it turn left, I denote it by -1. If it does not change, I denote it by 0. If it makes it turn right, I denote it by 1. Or if I'm going from very large to very, very large, I say it's +1. If I'm going from very large to large, I say it's -1. Of course, they may not be existing, in which case no changes made. So here, if there were 15 rules and each one of them had in these 5 inputs and 2 outputs, so there are these many genes. Each one of them will be either +1, -1, or 0. And my conventional genetic operators will solve this problem. And the third thing in my problem solving with genetic algorithm methodology, I have solved problem 1 here, where I have, for both these techniques, I have said what will be the individual representations strategy. I'm using the standard genetic algorithm operators, which is my second problem that I usually consider in my genetic algorithm problem solving methodology. The third is, of course, the fitness function. I made in some benchmark maps. I made multiple vehicles go by those benchmark maps. I noted performance in terms of the average time taken, in terms of collision, if it happened or not, and how much it happened, in terms of how much safety distances were violated, in terms of how much time the vehicle was in the wrong side. I simply added them up with penalties, and this becomes my fitness function for both these, for the rule optimization as well as the membership function optimization. And that's how the entire evolution would go about. Now I'll reset the graphics and I'll basically say what's happening out here. I fed in some human designed fuzzy inference system which might be suboptimal in some cases. I tuned in the rules. I got in a new set of rules. Now my membership function parameters which were best for the old rules will not be good for the new rules. So I tuned in the membership function parameters. Once I got new membership function parameters, I might be able to frame in better rules to suit those membership function parameters. I again tune rules. For the new rules, I tune in the membership function parameters. So I'm cycling across this membership function tuning and the rules tuning. By the way, there were only 5 cycles that were applied. It's a very computationally expensive task. This is what is computationally expensive simulating. So using these few cycles, I could generate in a good fuzzy inference system which locally optimized or which tuned in a human designed fuzzy inference system. And these are the results. As you can see, it was generated in the middle of the road. It was in the wrong side. It corrected its side and it traveled nicely. It corrected its side. It's avoiding some obstacle out here. 2 vehicles generated, one from here, one from here. They can avoid each other nicely. And of course, they are not actually avoiding each other. They are just correcting their side. And in correcting their side, they automatically avoid each other. This is the overtaking scenario. Now, these scenarios, they are optimized by the genetic algorithm. So even though I had taken wide margins initially, I had set wide thresholds initially. Overtaking was just possible. The genetic algorithm has played around with them, and it has only shown the scenarios which are in which overtaking is just possible. The closest one of them that I presented out in this video, and this one, of course, is the crossing scenario. So previously, I'll rewind it up again. This is the overtaking scenario. The next one is the when the vehicles place themselves parallelly. The road was wide enough for all three vehicles to get accommodated, and this is the vehicle following. Overtaking is not possible, and later on it becomes possible. And again, genetic algorithm has optimized all these scenarios to make it them just possible, and that's what's the crossing scenario. Uh, this is how the speed changes along with time. So whenever there's something ahead, it slow us down in speed in order to best avoid it. When I'm overtaking, then I can nicely have high speed, which is not the case when I'm following some vehicle. I'll have to reduce speed and then again increase when overtaking is possible. And that's what I said. Normally, I would like to always be at zero deviation from the road. I'll always like to be aligned at the road, but because the roads have turned, it this flickers around at a very small angle, say minus 10 to 20 degrees effectively, and it can be larger when there are obstacles when I need to change in my orientation large enough to avoid the obstacle and then maintain my deviation with the road. And this is again the angle of the deviation with the road. And that will be all for the presentation. Thank you.